Let's talk about hydrohalogenation, the addition of a hydrogen halide to alkenes, right? Your hydrogen halide is generally, to generalize it, it's generally written as HX, where X represents any halogen, right? The name of the reaction tells you what you're adding. You're adding hydrogen and a halogen to the carbon-carbon double bond in your alkene, right? So what happens in this reaction is that the hydrogen and whichever halogen it is added to the carbons of the carbon-carbon double bond. Of course, the carbon-carbon double bond will break to give you a carbon-carbon single bond. Then you add your hydrogen and your halogen. Let's take a look at an example. So let's say you're given this alkene, right? And you need to add hydrogen bromide to it. This is your hydrogen halide, which is why it's called a hydrogen halide. Now, in this reaction, what will happen, like we just said, is your carbon-carbon, and I'm going to call these carbons carbon 1 and 2. The double bond between carbon 1 and 2 is going to break, leaving you with a carbon-carbon single bond, right? Please put the hydrogens back because we didn't remove them. When you don't remove things, you must put them back, right? So we're going to put our hydrogens back. So carbon number 1 had 2 hydrogens. Let's put them back. Carbon 1 had 2 hydrogens. Let's put them back. Now, we need to add our hydrogen bromide. Now, in this particular example, it doesn't matter which carbon you put your hydrogen and your bromine on. Here's why. Because your alkene is symmetric, this is a symmetric alkene, and I'm going to explain what that means in a minute. This is a symmetric alkene. So it doesn't matter if I put my hydrogen on carbon 1 or carbon 2, you'll get the same product, right? Let's explain what we mean by a symmetric alkene. By the way, in this reaction, these two carbons of the carbon-carbon double bond where you could possibly add the hydrogen or the bromine, these positions are what we call vinylic positions. So let me label that. These two carbons are called, and these are the only two positions where you can add your hydrogen or your bromine. Let's go back to symmetric alkene. Now, a symmetric alkene, right, is an alkene in which the carbons of the carbon-carbon double bond has the same atom or groups of atoms bonded to it. Let's talk about what I mean. Let's find the carbon of the double bond, carbon number 2. These are the carbons of the double bond. Whenever I say carbons of the double bond, I'm talking about the two carbons that share the double bond. This carbon has 2 hydrogens on it. All right, cool. It has 2 hydrogens bonded to it. Go to carbon 1, the other carbon that shares a double bond. It also has 2 hydrogens. So it's symmetric because carbon 2, right, which is a part of the carbon-carbon double bond, it has 2 hydrogens. When I go over here, this carbon also has 2 hydrogens. So this is a symmetric alkene. So when you have a symmetric alkene, the position where you place your hydrogen and your bromine does not matter, right? Uh, Let me prove it to you. The name of this molecule is going to be, and I have to renumber for naming. So let's take out the numbers here. If I'm going to name, and you should remember this because I know you're now a pro at naming, it's going to be 1 bromo ethane. Now let's say I did the reverse and I put bromine on carbon, on this carbon. Let me take out the numbers too. So I'm swapping it around, right, from what we had before. Let's say I now put bromine here and the hydrogen here. The name of the molecule, because this will now become carbon 1, that's carbon 2, is still 1-bromoethane. So if you have a symmetric alkene, where you put the bromine or the hydrogen does not matter. Okay? Something to remember. As students, always remember that all the action is taking place at the vinylic position. If you don't remember that word, just remember all the action is happening at the carbon-carbon double bond, which means that anything you're adding must be added to either one of these carbons. Okay? Let us now look at an example where we have an asymmetric alkene, because if we have an asymmetric alkene, things change, right? So let's talk about the asymmetric alkene. So let's bring up this reaction. So once you have an alkene that is asymmetric, you now have to consider where to put the hydrogen and where to add the bromine. Now, firstly, let's establish that we have an asymmetric alkene. Carbon 1, 2, 3, right? So we do have an asymmetric alkene. Let's look at it. Find the carbons that share the double bond, okay? On carbon 1, I have only 2 hydrogens bonded here. But let's look at carbon 2. I have a hydrogen. This is also bonded to carbon 2, so I have a hydrogen and a CH3. This is an asymmetric alkene. It's an asymmetric alkene because, as you can see, this carbon has 2 hydrogen, this carbon has a hydrogen and a CH3. So the groups that are bonded to carbon 1 are not the same as the groups that are bonded to carbon 2. That's how I know I have an asymmetric alkene. Okay? So with that asymmetric alkene, the question is, okay, what am I supposed to do? Where do I put the hydrogen? Where do I put the bromine? Now, there's this guy, and you're going to have to remember his rule. There's this guy called Markovnikov. I honestly think this is how Markovnikov got his PhD. And I like to call him Mark for short. Mark did some work and realized that if he adds the hydrogen of our hydrogen bromide to the carbon of the carbon-carbon double bond with the most hydrogens, that's the product that he observed, right? So we're going to follow Markovnikov rule. I will explain why Markovnikov is right when I do the video on mechanism for an alkene plus HX, right? Hydrohalogenation mechanism, I'll explain why Markovnikov made sense. But you need to remember this man's rule because a couple reactions will follow his rule and you have to follow the rule, right? So according to Markovnikov, the hydrogen, which is this hydrogen, will add to the carbon of the carbon-carbon double bond with the most hydrogens. So if the hydrogen is adding to the carbon of the carbon-carbon double bond with the most hydrogens, right? Clearly, the Br is going to add to the next carbon. We can also look at this as the hydrogen. So Markovnikov rule can be read two ways. I honestly prefer remembering this way because it's easier, right? The hydrogen will add to the carbon of the carbon-carbon double bond with the most hydrogen, right? And then clearly, whatever halogen you have will add to the next carbon of the carbon-carbon double bond, right? Because all the action is at the carbon-carbon double bond. Markovnikov rule is also interpreted as the hydrogen will add to the least substituted carbon of the carbon-carbon double bond, and then your Br in this case will add to the more substituted carbon of the carbon-carbon double bond. Let's talk about how would I identify the most substituted or the least substituted. I mean, clearly, this interpretation is much easier, which is why I would recommend you remember that, but you also need to be able to recognize more substituted and less substituted carbon. So let's talk about which one of these is more or less substituted. Okay, so carbon one, right, has that's a hydrogen, that's a hydrogen, right? Carbon number two has a hydrogen and a group that is not a hydrogen. Okay, it's a substituent. So carbon number one has how many substituents? Zero. Hydrogen is not a substituent. So over carbon one, I have zero substituents, zero sub, right? Let's go over to carbon two of the double bond. I have a hydrogen and I have CH3. I have one substituent. One is greater than zero. So this carbon is your more substituted carbon. Okay? So all you're doing when you're looking for which carbon is more substituted, look at the sub, count the number of substituents on it. Go back to the carbon of the carbon-carbon double bond. This carbon has no substituent bonded to it. This one has a hydrogen and a CH3, so it has one substituent. One is more than zero, okay? So this is our more substituted carbon. All right, cool. I like to keep it simple. So I just remember that the hydrogen adds to the carbon of the carbon-carbon double bond with the most hydrogen. That's the easiest way to remember Markovnikov rule. So let's talk about what happens when our hydrogen and our Br gets added here. And if you notice, I'm not talking to you about nucleophiles and electrophiles. I'll do that in your mechanism. But to simply, if you're given a question and they ask for the product, you don't need to write a mechanism. If you have the mechanism in your brain, honestly, it makes it easier for you. But hey, let's do this because we're not writing the mechanism right now. So draw carbon one, two, three, right? Put your carbons back because we did not lose them. You can't just get up and throw things away in chemistry. Something has to happen for you to say, okay, we lost the carbon or we lost the hydrogen, right? Let's number carbons. So on carbon three is not getting any action. It's not a part of the carbon-carbon double bond. Put the hydrogens back, right? On carbon two, this hydrogen is still present. I didn't lose it. So put it back. And on carbon number one, we have two hydrogens, right? We didn't lose these. Please put them back. Now, let's talk Markovnikov. Markovnikov states that the hydrogen is added to the carbon of the carbon-carbon double bond with the most hydrogens bonded to it. Carbon number one has two hydrogens bonded to it and it's directly bonded. Okay, so carbon one has two hydrogens. Carbon number two only has one hydrogen directly bonded to it. Directly bonded in this direction, the carbon two is a carbon. Please don't make this mistake. These three hydrogens are on carbon three, not carbon two. Okay, so when we look at carbon one, it has two hydrogens. Carbon two only has one. So based on Mark, right, your hydrogen is going to add to carbon number one and your Br is going to add to carbon number two, right? So because of this, we say that this reaction is what we called a regiochemical reaction. I'm going to use RX for reaction, right? Because your hydrogen adds to, if you want to look at it this way, a particular region in of the carbon-carbon double bond, right? Because remember, the hydrogen is adding to a particular region in the molecule. So we say that because the reaction is regiochemical, which means that it's in the word region. Regiochemical. It means that your chemical, in this case, which is the hydrogen or the bromine, is adding to a particular region, right? We say that this reaction is what we call regioselective. And chemists are not crazy, right? We use words in English that actually mean something. Regioselective, it means that it's selecting a particular region. The hydrogen is selecting a particular region to be added to. Regioselective can also be explained a different way, right? And let me explain that too. So some textbook will look at regioselective as, which is the same concept, right? The fact that regioselective just simply means that in a reaction where you can form possibly more than one product, only one product is observed, right? You can have a reaction where you can have more than one product, but only one product is observed or only one product is formed, even though two or three is possible. Let me use this reaction up here as my example. So here, I'm going to bring the words down. So let's look at regioselective and explain it from being able to form more than one product. All right, cool. So let's do this. So this is our first product. And I guess you can't take it outside the page. All right. I promise I'm going to get this now. It's okay. Let's just move it down here, right here. Good. Here we go. Let's talk. So remember, right? We already did this reaction, right? Following Markovnikov rule. And Markovnikov is right, okay? I will explain why when I do the reaction mechanism. But he is right. Just accept that like you accept 1 plus 1 is 2. Let us explain regioselectivity, right? So regioselective means this reaction, which is true, can form two products, but only this product is observed. This is the only product that is formed, right? Your second product, if we disobey Markovnikov rule, the second product would be, this is carbon 3, carbon 2, carbon 1, right? Let's put our hydrogens back. And then let's add our hydrogen or bromine. We're going to disobey Markovnikov rule, right? If we disobey Markovnikov rule, the hydrogen is going to add to carbon 2 and your Br is going to add here. These are two different products. And if you're ever like, how do I know these two things are different? An easy way to do is name them, right? And if you look at it, you should see that they're different. The bromine is on carbon 2 here. Here it's on carbon number 1. If you name them, they will have different names. And I know you guys are great at naming by now. So go ahead and name them. They're two different products. This is product A and this is product B, right? Now, this is what we mean by when we say in a reaction that is regioselective, one product is formed over the other. When this reaction is carried out, this is formed in 100%. This is what is observed. This is not even formed. Okay, so remember that's what regioselective means. So when you make your little flashcards, when you write a reaction like this, you can draw a skeleton for the alkene and just put plus HX where X represent any halogen. You know the double bond breaks, leaving you with a carbon-carbon single bond, and this adds. So under this, now you write some little notes. You write that the reaction is Markovnikov, and you please remember what that means. That is your Bible to alkene reactions, because a lot of reactions are marked, okay? And we also have non-mark ones. You write that it's mark. Mark literally covers regioselective. Because remember, it's because of Mark and what he said why we know the reaction is regioselective, where the hydrogen adds in a specific place. That's how you make your little notes. Here's the thing. With organic, You have to memorize some things, but there a big part of it is concept. So it's two things together, memorization and concept. The concept here is you remembering what Mark says. Yes, sorry. The memorization is you remembering, memorize what Mark says. The concept is you being able to apply it to it. Doesn't matter which alkene I give you. All you need to do is be able to identify which carbon has the most hydrogens, right? So pick something. It's either you're gonna remember that the hydrogen adds to the carbon with the most hydrogens, or you're gonna remember that the hydrogen adds to the least substituted carbon. I would remember that the hydrogen adds to the carbon with the most hydrogens, right? And clearly, if I add something here, the only other place that the bromine or whichever halogen could add is right here. Another thing, concept. If I give you HCl, is the same thing going to happen? Or if I give you HI, okay? So memorize concept, because the thing with organic is structures will change, but just trust me one time. If you get what I'm saying, it doesn't matter what alkene you have, you'll be okay.